Good afternoon for those of us who are meeting by Zoom on January the 25th. I would first like to welcome Kent Peacock from the University of Lethbridge, our speaker today. I'm pleased to welcome everybody on behalf of KCOR who's able to join us live. And I'd like also to welcome those who watch on KCOR's YouTube channel at any time in the foreseeable future. It will be there. Now, in 2015, the political leaders of the world, if leader is the proper term, settled on the 2-degree target with a sort of wish for 1.5. We're very close to blowing past the 1.5, and Kent is going to help us understand where those numbers came from and his take on the matter. So, Kent, welcome. Over to you.
Okay, well, thank you very much, and thanks to KCOR for having me on and allow me to talk about these very interesting matters. So, and as again, one of the problems is when you want to talk about climate, you think you have a definite topic in mind and it explodes on you because there's so much to be said and so many things interconnect. But I'm going to sort of start off with a definite focal point that really jumped out at me last fall that I think people might be interested in, or I think people need to know about, which is a report that was issued last fall in mid-November by the International Cryosphere Climate Initiative on the state of the cryosphere 2023. So I want to talk about that. And then John mentioned this question of the 2 C supposedly a safe guardrail. At least that's how it was originally marketed a long time ago. And I guess the starting point for what I want to say is that we now have extremely good evidence that that's not a safe guardrail at all. It's anything but. So we want to, first of all, I just want to try and explain why that is the case and a little bit of the history behind it. Okay, so here's what I think everyone needs to know on this one slide. And to anyone out there who doesn't have time to watch the whole video, this slide is the lead. And if you stick with me for this one slide, you'll see the essential point of the talk that I'm giving. And then after that, I'm going to give more background, more details. So here's what everyone needs to know. So I'm quoting from the State of the Cryosphere 2023, and this is a thing put together by a very long list of senior glaciologists, mostly, or people who work in related aspects of climate and earth science. So they say a compelling number of new studies all point to a threshold for both Greenland and parts of Antarctica that well below 2 C, committing the planet to between 12 and 20 meters of sea level rise if 2 C becomes the new constant Earth temperature. And if they're right, well, pretty good chance they're right. This implies that 2C is not a guardrail, as it's often been described. It's not a guardrail beyond which the effects of carbonization will become unacceptable. Rather, it's a point at which climate catastrophe is guaranteed. So, so the report plus some other evidence I'm going to bring put before the court here imply that current climate agreements, which are bent on staying within 2 C and aspirationally holding to 1.5, are hopelessly inadequate. And what really struck me is that this State of the Cryosphere report, which was published just a few days before COP28 got started in November, has received almost no notice or discussion in major media outlets. I mean, there's a couple of YouTube videos on it by a couple of scientists, and Dr. Gilbs has a nice little one on it. There was something on it in the Guardian, but I sent an op-ed to the Globe and Mail. They definitely weren't interested. Maybe it wasn't written well enough, but somebody it was just no mention. So right when the climate talks are getting started, along comes a piece of scientific evidence that invalidates the fundamental premise of those talks, and it didn't get mentioned. Now, so if you dig back into the literature a little bit, you find some interesting things. So I'm going to do a little dive into the next few slides into some of the history of people's concern with ice, right? So going back to 2013, I discovered this paper published in Proceedings of the National Academy of Sciences in 2013 by Foster and Rowling, relationship between sea level and climate forcing by CO2 on geological timescales. So they're sort of going back several million years and trying to basically plot correlations between sea level and global CO2. And what they find is that the bit I put in red here, our results imply that acceptance of a long-term 2-degree C warming, which is equivalent to CO2 between 400 and 450 parts per million, would mean acceptance of likely, with 68% confidence, long-term sea level rise by more than 9 meters above the present. Further studies may improve this estimate. Now, here's the catch. This paper was published 2 years before the Paris Agreement of 2015, which set the 2C as the world's climate policy goal. So this was published in a top journal, PNAS. As far as I know, it's never been refuted or shown wrong or anything. So it was known already by the time they started that meeting that their nominal policy goal was hopelessly inadequate scientifically. We can talk about why that might have happened later on. Now, there's also, I want to mention warnings from James Hansen. Hansen, the former head of NASA Goddard, now runs an independent climate research center at Columbia University, has been warning for decades of the risk of ice sheet collapse. Here's from something he wrote in a very important paper of Hansen's called Scientific Reticence and Sea Level Rise from 2007. The nonlinearity of the ice sheet problem makes it impossible to accurately predict the sea level change on a specific date. And later on, I'm going to explain a bit more about what that means. However, as a physicist, I find it almost inconceivable that business as usual climate change would not yield a sea level change on the order of meters on the century timescale. So you're forced to sort of rely on order of magnitude estimates because the detailed mechanics are so difficult to predict. But you know, there's a lot of sea level rise in the pipeline, and Hansen and his colleagues state that they're currently working on a paper soon to be presented, we hope, called Sea Level Rise in the Pipeline. And so I'm watching out for that paper. So Hansen set the bar very high. So in this 2007 paper, he said the threat of a large sea level change is the principal element in our argument that the global community must aim to keep additional warming less than 1°C above the 2000 temperature, which is roughly equivalent to about 1.4 or so above the IPCC baseline. Of course, you have this problem whenever people talk about temperature anomalies, you always have to say, what baseline are you talking about? So the IPCC numbers, as far as I know, rely on 1850 to 1900. And even 1°C may be too great. In turn, this implies a CO2 limit of about 450 ppm or less. Now, when I checked Tuesday morning, we were at 422. You can just Google Keeling curve and you can easily find the updated readings from Mauna Loa. So such scenarios are dramatically different than business as usual, requiring almost immediate changes to get on a fundamentally different path. And then in 2008, Hansen and a bunch of colleagues published another paper called Target Atmosphere CO2, Where Should Humanity Aim? And they argued that CO2 concentration should be reduced to no more than 350 parts per million, but likely less than that. So later on, I'm going to come back to this question of CO2 concentration. But first, we're mostly going to talk about ice and why ice is so important. So we go back a few more years to this gentleman here, John Mercer, a glaciologist who was at Ohio State University and some years ago when I was going to climate conferences and starting to get very interested in the ice sheet problem, a climate scientist said to me, you know, you really should read Mercer. Everybody's got to read Mercer. So I read Mercer. So in 1978, you know, back when Saturday Night Fever was the hot movie, right? In 1978, Mercer published a paper in Nature called West Antarctic Ice Sheet and CO2 Greenhouse Effect, a Threat of Disaster. And he made the following statement: if the CO2 greenhouse effect is magnified in high latitudes, as now seem likely, deglaciation of West Antarctica would probably be the first disastrous result of continued fossil fuel consumption. Now, this may seem a little less shocking of a thing to say today, but in the 1970s, this was a bit of a stretch for most glaciologists, because what I've been told is that the sort of assumption was that, yes, we're very worried about greenhouse effect and global warming, but don't worry, the major ice sheets will take thousands of years to melt. This was kind of the received view for a long time. According to what I've heard from one glaciologist, even into the 1990s, it's like, yeah, Greenland is going to melt, but it's going to take thousands of years. Well, what Mercer realized is there'd been a bunch of work done on studying the dynamics of ice sheets at this time in the 1960s and 70s. And he realized that that's not necessarily the case, that some of the ice sheets, particularly West Antarctica and certain parts of Greenland, are so sensitive to climate change that they could be capable of melting down or even collapsing so quickly that they would be one of the first major effects we would observe of greenhouse warming, not something that would happen thousands of years down the line. Now, as we know, he said, if the effect is magnified in high latitudes, well, now there's a thing called Arctic amplification, which is now very well confirmed, and we know that depending on what region you're in, the Arctic is warming between 2 and even up to 6 times as fast as the global average warming. Mercer also said, in one of the warning signs that a dangerous warming trend is underway in Antarctica will be the breakup of the ice shelves on both coasts of the Antarctic Peninsula, starting with the northernmost and extending gradually southward. I'm sorry, I forgot to put a map of Antarctica in this presentation, but if you know what Antarctica looks like, it has a sort of a finger of land pointing up roughly at South America. That's the Antarctic Peninsula. And because it's a little farther from the pole, it's a little warmer there. So anyway, Mercer made this prediction in 1978. Of course, most people will know in 1995, an ice sheet called Larsen A, which is the one closest to the tip, simply blew apart overnight. Just one morning it was gone. And then in 2002, a somewhat larger ice sheet called Larsen B shattered in a few weeks. And there's some very good NASA satellite pictures of that happening, which I understand some climate deniers believe was faked by NASA, but it wasn't faked by NASA, folks. It really happened. And then some large chunks have broken off Larsen C, but much of Larsen C is still intact, but some big chunks have broken off it. But the point is, Mercer called it. He said this roughly 20 years before it happened. Mercer said these ice sheets are going to break down. And the general response to Mercer at the time, from what I've been told by most other glaciologists, is, yeah, he's a really good glaciologist, but he's just a little over the top on this. We think this is slightly alarmist. And that now it's turned out that he called it. So he also correctly predicted that the center of the West Antarctic ice sheet would begin to thin, and it's been doing that. So sea level rise is a really big concern. And last year, Mr. Guterres, the Secretary General of the UN, warned seas may rise to, his word, unthinkable levels and threaten a mass exodus of entire populations on a biblical scale. Mr. Trump thinks that sea level is going to rise, I think it's 1/300th of an inch in 300 years or something like that. But no. So the question is, what levels of sea level, what risks and how much sea level rise do we actually face? So a lot of people know these numbers, but it's worth just putting them up here for reference. Okay, so if all of the ice in the world were to melt, current estimates, it would raise sea level by between 65 and 70 meters, not millimeters, meters, 200 and something feet. Greenland, about 7 meters, all by itself. Antarctica, all of Antarctica, something like 58 meters, maybe a bit more, but they still haven't really been able to identify all of the ice that's buried down there in all the valleys and so forth yet, but roughly 58 meters. Various mountain glaciers and ice fields around the world make up most of the rest. And then also you get a certain amount of sea level rise due to simply to thermal expansion. Water expands when it gets warmer. And if depending how much of the ocean, how much it gets warmed up, there will be some sea level rise due to thermal expansion as well. And worst case scenario could even be, I'm just guessing, a meter or so as well. So roughly 65 to 70 meters in if everything melted. Now, most people would agree, look, even Hansen would agree, yeah, that's going to take some thousands of years for all of that to happen. But we could have very, very damaging levels of sea level rise without having to melt everything, right? So the question is, how fast could it occur? So I'm just going to tell you about a few little things that I've learned about glaciology. I mean, and I emphasize, I'm not a glaciologist. This is not glaciology 101, because I wouldn't even be qualified to teach that. This is more like kindergarten glaciology, which even a philosophy professor can understand. So what we'll see once we sort of go through some of the mechanisms or some of the physics of this is that, in a very important sense, the question of how fast is close to meaningless. There is no longer any scope for delay. But anyway, so very, very quick review of a couple of facts about ice that everybody needs to know. Okay, so different kinds of ice. Let's talk about that. So for our purposes, and this is of course grossly oversimplified, there are three main kinds of ice in the world. So there's ice on land, which are the ice fields in places like Greenland, mountain glaciers, land-based ice caps, such as the ones we have here in Alberta and BC. Then there's floating ice, which can be either sea ice and then ice shelves and ice tongues. And ice shelves and ice tongues, they're often several hundred meters thick, and they basically produced by large glaciers flowing out over the sea and floating on the sea, whereas sea ice is produced by seawater freezing. And of course, I'm, again, grossly oversimplifying. But then there's a third kind of ice that some people don't fully understand. And when I got interested in this, the relationship between ice and climate issues several years ago, I didn't quite understand what a marine ice sheet was either. It was a bit of a revelation for me when I sort of did some reading and talked to some people and started to get a grasp of what this is all about. There's a thing called a marine ice sheet. And for reasons I'm going to explain, it's the wild card. It's the thing we really need to understand. Okay, so let's talk about how things can melt. So melting by land, in a sense, this is the simplest thing to understand. If land-based ice melts, it's simple. Sooner or later, the water is going to end up in the sea. And yes, in principle, some could evaporate and turn back into snow, but you can very often get scenarios where the melt rates can greatly exceed any possible evaporation or recondensation, and that's certainly what's happening in Greenland now. So it's a melting of the land-based ice is a very major mechanism of mass loss in Greenland these days, especially in the summer. And you've all seen those pictures of the blue lakes on Greenland, the blue lakes of meltwater, which are exceedingly dangerous because they have sinkholes in them called moulins. And every now and again, in a completely unpredictable way, the whole lake will go down that hole. And you don't want to be on the water in a boat when that happens. Okay, melting by sea. So if floating ice melts, it does actually raise the water level slightly, not a lot, but not everybody understands this. I actually saw a website yesterday by a glaciologist who didn't seem to realize this. But there's a nice page on NASA explaining how this works. And it's not a major effect, but in fact, when you have fresh water floating on salt water, because fresh water is at a lower density than salt water, when the ice melts, it very slightly raises the water level. Whereas if you have fresh water in fresh water, like an ice cube in your drink, when the ice cube melts, it doesn't change the water level. And if you want to look into that, you can look that link up. However, melting of sea ice has three very major and very important effects, at least three that I'm aware of, major effects on the Earth system. And these are the ones that really matter. So first of all, open water absorbs much more solar radiation than ice. So ice obviously is shiny, it's white, it's reflective. And the technical term is albedo, which means whiteness, just a Latin term that means whiteness. And so open seawater has a much lower albedo than snow or ice. So when ice melts, it causes more heat to be absorbed by the oceans, which ultimately gets distributed to the whole Earth system. So one of several examples where warming causes more warming, right? That's the first point. Also, the next thing worth got to mention, ice shelves buttress the land-based and marine terminating glaciers behind them. And they sort of act like corks in a champagne bottle. They slow down or stop the flow of the glaciers behind them. And when the shelves disappear, this happened with Larsen B, the glaciers can flow into the sea much faster. And I think the glaciers behind Larsen B, figure I recall, is 6 to 8 times faster than they were moving and flowing before the ice shelf disappeared. And of course, this can raise sea level because you're bringing ice into the sea that was above sea level. And a third point, which is very important, and I think still, my guess is not well understood, the loss of sea ice and ice shelves may have disastrous effects on various kinds of marine biota and marine ecosystems. For example, underneath the so-called Ross ice shelf. So there's a huge ice shelf in Antarctica, roughly south of Australia and New Zealand, called the Ross ice shelf. It's about the size of France. It's absolutely huge, about 800 meters thick. And there's an extremely rich ecosystem underneath it. And if the ice shelf disappears, that ecosystem will be gone. But third kind of melting, again, this is the one that's not as well understood, melting below the sea. So we have these things called marine ice sheets, and what they are is gigantic masses of ice jammed into basins, and these basins often they are deep valleys, sometimes carved into the Earth's crust, sometimes going down 2.5 or in one case in Denman Glacier in Antarctica, 3.5 kilometers below sea level. So you imagine this giant basin, and then it's got some kind of channel leading to the open sea. The glacier tries to flow out the channel, and so at the end of the channel, it's in the open sea. So these are called marine terminating glaciers, and very often there's a major ice shelf out in the sea at the mouth of the giant fjord where the glacier flows out. And the thing about these marine ice sheets is that we know they can be stable for thousands, tens of thousands of years if the climatic conditions are right. But if forced by warming and if the ice shelves break down, there is evidence that these ice basins can collapse very, very rapidly, and possibly in bursts that would be impossible to precisely predict in advance. And I'm going to explain a little bit more about that. And here's just a few of the important ones. So there's, everybody's heard of the Thwaites Glacier, the so-called Doomsday Glacier. Well, behind the Thwaites Glacier, inland from it, is a huge central basin in West Antarctica called the Bentley Trench, named after a glaciologist, of course, which my understanding is good for 3.3 meters of sea level rise. Then there's a couple of very, very large glaciers in East Antarctica. Totten Glacier, Denman Glacier get mentioned the most often, each of them good for several meters. And there's a few glaciers in Greenland, which are also good for 0.5 meter, maybe more each. for similar reasons. So what's going on here is try to understand the simple physics behind this. And the way I understand it, and I'm sure this is a little bit oversimplified, but this is again, a philosopher's way of understanding what's happening here. There's a technical term used, ice over flotation. And the way to picture this is just imagine a bathtub with maybe a foot or so of water in the bathtub, and you've got a stack of ice. Remember those old-fashioned ice blocks that are about a foot on a side, right? And imagine a stack of ice blocks sitting in this bathtub, and there's quite a few ice blocks stacked right up. Well, that stack of ice blocks is going to be too heavy to float, so it sits on the floor of the bathtub. And that's an example of ice over flotation. Simply that there is more ice than can float in a given footprint and depth of water. If you made the water deeper, you could maybe float a bit more ice and so forth. And then what happens is, if you can keep on piling these blocks of ice up as long as you want, but if they melt, they will obviously raise the water level. Now that's what's happening in these giant marine terminating glaciers, where you have these giant they're marine ice sheets, where you have a huge basin filled with vast amounts of ice over flotation. So roughly again, the way I understand it, and if there's any real glaciologists out there, I sit to be corrected on this. The basic picture is that over many, many millennia, snow builds up and compresses into blue ice within the basin, and it's very simple. It builds up faster than it can flow out, because the entrance of the basin is only so big. So you get an accumulation of ice, and in principle, it could just build up arbitrarily high. Now, in fact, ice is in fact a viscous fluid, and it does slowly flow to the sea. So there's always a balance between ice building up and ice trying to flow away. But still, on a lot of these glaciers, that you can get colossal amounts of ice building up, equivalent to many, many meters of sea level rise. And the other interesting thing that happens in some of these basins is that the ice is so massive that it actually compresses the Earth's crust, which makes the basins deeper. But this has some interesting side effects. So, okay, so I'll get back to that. The other interesting thing that happens is that this is true for any glacier that's in what they call a fjord, a narrow channel. As the ice over millennia advances, then it retreats, then it advances, then it retreats. The glacier will bulldoze out these deep fjords, and that's called over deepening. The glaciers carve out the fjord. So every time the ice advances, it makes the fjord a little bit deeper and removes more and more of the obstacles to the flow of the ice. So the next time you have a melting or a warm period, it makes it easier for seawater to get underneath the ice. Right. And if you look at these West Antarctica, again, we don't know for sure, but there's evidence that there have been something like, well, you've probably heard, if you took sort of high school geography, there's been something like 18 ice ages in the last 2 million years. And that implies roughly 18 periods of glacial advance, where these glaciers have been able to carve out or over deepen their channels. So West Antarctica, as I say, mostly a grounded marine ice dome, this huge central trench up to 2,500 meters below sea level. And in the middle of it, it's about 1,000 meters above sea level. That's how much ice is built up over millennia. So there's a very good article by Jeff Goodell in Rolling Stone, if you want to read a bit more about this. Again, as long as these ice sheets remain cold enough and they're protected from the open sea, they can remain stable for tens of thousands of years. But what happens if they become exposed? So there's quite a bit of evidence now, which comes partly from Paleoclimate, which is the study of ancient climate conditions, and partially from physical analysis, that if if you can get relatively warm seawater, can get access to the base of such ice domes, and relatively warm seawater means 2 degrees C. Water that would be far too cold for humans, but 2 degrees C seawater is death to an ice sheet. And if seawater can get access to the base of the domes under certain circumstances, which still remain to be not fully understood, they can collapse catastrophically, possibly even within a few years, although this remains a matter of debate and investigation. And you're going to hear different stories from different glaciologists. This is an area that my sense from talking to people and from the literature that they're still not sure about this. There's still disagreement at the expert level. But there's a term that's used for this. There's a special term, marine ice sheet instability. And now you can think of it as a general term for the instability of these marine ice sheets. But it also refers to something quite specific that was actually discovered by a number of glaciologists in the 1960s. So if you, actually it'll make more sense when I show the next slide, so I borrowed this slide from a very nice website called Marine Ice Sheet Instability for Dummies. And it's worth looking at if you're interested. But the key point here is, here's a giant ice sheet. There's a model for many of the big glaciers in West Antarctica. Here's sea level. Okay, so you can see the ice sheet goes up quite a bit above sea level. Here's your ice shelf, and in our warming area, the ice shelf keeps fracturing and breaking off. So you get so the front of it's called the calving front, because that's where the calving is this process where giant icebergs break off of an ice sheet. So this is the calving front, and calving front keeps moving further and further back. And down here you have what's something called the grounding line, which is the point at which the ice sheet sits on the bed of the seafloor. And what you hope is there's some nice little mountains and rocks and things in here that are going to impede the flow of the ice. Because the ice, remember, is dynamic, it's flowing. Even under ideal conditions of when we have no problems, ice is always flowing toward the sea. And the question is how fast, and does it get replaced? And so if you have a nice little mountain down here, that's called a pinning point. And so one of the things that people are trying to understand in their surveys now is they look at glaciers like Thwaites Glacier, and they're trying to see how many pinning points are down there. And with regard to Thwaites, the answer is not enough. But one of the important things to grasp is you notice the slope goes down. It's called a retrograde slope. So this, when you're very close to the mouth of the glacier, this might be, I don't know, 200, 300, 400, a few hundred meters deep at the most. And then this can plunge down to a couple of kilometers. So you get this downward slope. And the crucial point is, the crucial point is that as the grounding line moves down the slope, the ice collapses faster. And this was discovered in the 1960s. And I think this is really was the red flag for John Mercer when he was just in his mind spelling out the implications of this fact that the ice is extremely unstable once it starts, so if it's kind of everything stays out about here, you're fine for a long period of time. But if the calving face and the retrograde and the grounding line get too much inside the slope, it just goes faster and faster. It's a positive feedback process. Now there's several other processes that can also take effect. Now something that's been discovered more recently is something called ice cliff instability. And I had the privilege of hearing Richard Alley give a talk on this about 10 years ago, and it really opened my eyes, and sort of walked away going, holy smokes, I had no idea. So here's the thing, glacial ice is not very strong structurally as compared to rock. It fails both in tension and shear. Ice is not physically strong enough for there to be a calving front much more than 135 meters high. 100 to 135 meters. So if you see those giant glaciers like the Jakobshavn, the big one in Greenland that produces those incredible calving events, the ice front's 100 or so meters high, and that's it. Ice can't be any higher than that. It's not strong enough. But Richard Alley made a very profound observation, very simple observation. Go back to my description of the Thwaites Glacier. The central basin is 1,000 meters above sea level. So if the calving front eats its way back through the glacier and advances into the central basin, you're going to have a calving front 1,000 meters above sea level. But that's impossible. It can't stand up. So it's going to come down like a house of cards, perhaps extremely quickly. And we don't know how quickly. This is something we must presume this has happened at times in the past, like in the ends of other ice ages, but it's something that's obviously never been observed by anyone in modern times. And you get other factors too. So there's actually pressure within the ice, which actually tends to, Rich Alley explained to me, it's sort of analogous to rock bursts in a quarry. Sometimes the ice will literally just explode out just because of the internal pressure. So it's not out of the question that the whole Bentley Trench could be hollowed out in a matter of months, which could cause literally meters of sea level rise around the world, like a tsunami that does not go away. Right? And it could take a very short period of time. We don't know. All we know, so we don't know when it could happen. We don't know for sure that it could happen, but we know that it's on the table. But this has to be taken very seriously as a possible thing that could happen. Now, very quickly, I won't spend too much time on this. There's a number of other feedback processes as well that also accelerate ice sheet collapse. So obviously there's just straightforward melting, which is more important in Greenland than Antarctica right now. There's a thing called hydrofracturing. What that means is you get big crevasse on the surface of the glacier, and if in a warm spell, it fills up with water. Water is denser than ice, so it's just like when you're splitting firewood, it literally wedges the ice apart, obviously contributing to collapse. Now, the other thing that's been discovered quite recently, just in the last couple of years, is that in the ice shelf coming out from Thwaites, there are crevasses and cracks in the underside of the ice shelf, and warm water is getting into them and greatly accelerating the breakup of the floating ice, the ice shelf. And of course, again, this is sort of like driving a wedge into the ice shelf. And they're pretty sure now that the latest studies done in Thwaites indicate that the ice shelf on Thwaites may be mostly shattered within 5 to 10 years. And then at that point, what happens? Well, you still have the glacier. You're not into the Bentley Trench yet. You've still got the glacier there, but obviously it's going to start to flow faster, and that calving face is going to start eating its way back into the glacier. And how long will that take? We don't know. Another interesting thing that happens, which Richard Alley explained to me, is that tides cause the ice shelf to bend up and down. Okay, so if I can do this right. So imagine my hand here is the ice sheet, the glacier, and it's sitting here on the grounding line, and then tides pump the shelf up and down like that. And it acting like a giant bellows, literally pumping warm water underneath the ice sheet. So that's another interesting thing that can happen. And to add insult to injury, glacial ice is, of course, fresh water. When fresh water mixes with salt water, it releases heat. How important is that? I don't think they know, but it's in the mix. And then just one more thing to make it interesting, there's this issue of what's called isostatic rebound. So weight of the ice holds the Earth's crust down. If the Bentley Trench it started to melt beyond a certain point. Somebody did a study in this recently, and I'm sorry, I don't have the link, didn't get the link for this. And if the Bentley Trench, too much of it melts, the bedrock underneath springs up like a trampoline and expelling water and ice in all directions. So you have So again, and again, the time frame for that might be longer, but they don't know for sure. All they know is that you have a number of processes whereby marine ice sheets, again, can be stable for a very long time if everything's copacetic. But if they have a chance collapsing, if it's too warm, and if they lose their ice shelves, then there's a number of these processes that kick in that all tend to accelerate the breakdown, possibly quite dramatically. So this is when Hansen was talking about non-linearities, that's the sort of thing that it points to. So again, how fast? So this crazy collapse of the Thwaites calving front, how long could that take? We just don't know. But here's the real problem for policymakers. The chain of events that could trigger that catastrophe could be set in motion many years before the event itself occurs. So if the calving front gets too far into Thwaites Glacier, even if we reduce emissions, we recycle all our beer cans, you do everything that you should do, right? You might not be able to stop this process once it gets started. It's like it's like an avalanche at a certain point. Sorry, you can't stop it. The only thing you can do is get the heck out of the way. And again, this hasn't been studied. We don't know. There's another paper on glaciology, which again, I apologize, I don't have the link for, but published fairly recently, where a number of glaciologists just point out that it's weird how few people are actually working on this. You've got thousands of hedge fund managers out there, right? And so forth, but all around the world, a handful, 20, 30, 40 people with PhDs working on ice sheet collapse and trying to understand it. So, but this illustration brings us to the more general discussion of climate policy. And something that sort of jumped out at me is that there's an interesting parallel between nuclear brinksmanship and what I'm going to call climate brinksmanship. So brinksmanship says, how close to the edge can we skate? It's like the proverbial game of chicken, where two teenage boys hyped up on testosterone drive their pickup trucks towards each other and trying to see who's going to veer out of the way at the last minute, right? So we're playing nuclear chicken. We're also playing climate chicken, except the difference is with nuclear chicken, you're facing off against other nations. With climate chicken, you're facing off against the Thwaites Glacier. And it's just going to do what it's going to do. It doesn't really understand our games. Okay. So what I would say is that our current climate policy, it sort of gives the pretense of being based on sort of very sober cost benefit analysis. It is in fact a form of high stakes gambling. And that's what we're seeing now. Okay, so just another thing that everybody should be aware of. I won't spend too much time on this, but the gist of it is there are things, again, called paleoclimate studies, where people have studied ancient climates going back millions of years. And one of the things they're looking at is correlations between sea level and carbon dioxide levels. So our present level, around 420, is actually comparable to the Pliocene epoch 3.5 million years ago. Now, again, the reasons for the carbon dioxide being there are very different. So there are disanalogies, but still, it's worth looking at these numbers. If paleoclimate trends are relevant, we have enough CO2 to take us back to Pliocene climate conditions. But how long would it take for the atmosphere to come to equilibrium? So yeah, during meltdown of the last glaciation, about 11,000 years ago, there was a period, it's called meltwater pulse 1A, where the period of about 400 years, where sea levels rose several meters per century, 3, 4, 5 meters per century in that period. So we know that this is physically possible. And they think that this was due to precisely the mechanism I was describing a couple of slides ago. Major marine ice sheets collapsing very suddenly when the warming got beyond a certain threshold. And as most people will know, sea level is now something like 120 meters higher than it was during the peak of the glaciation. And it's very, very important to realize that there's nothing sacred about our present sea level. Sea level varies all over the place and in the past. And the fact that our sea level has been relatively stable for about 10,000 years is, as far as we know, essentially just a matter of dumb luck. So there's a very good paper published by Grant and a list of co-authors in Nature in 2019, where they study this and they say, although ice sheet, ocean, and continental geometries were subtly different during the mid-Pliocene, our results suggest that the major loss of Antarctica's marine-based ice sheets and an associated global mean sea level rise of up to 23 meters is likely if CO2 partial pressures remain above 400. So, of course, the interesting question is, how relevant is that? As they say, the world was a different place during the Pliocene era, but still got physics going here. So how much could sea level rise this century? So even the most conservative estimates have been steadily rising upward. Most glaciologists would estimate on the order of a meter or so. I think Hansen and a few others estimate several meters as a worst case scenario, because of course it depends to an important degree on the emissions pathway that are followed. But you have to ask a question of principle here. Should we plan on the basis of well-informed worst case estimates, or most probable or average estimates? Now, I used to teach engineering ethics a long time ago. Hint for the class: an engineer must design a bridge to be strong enough to withstand the maximum load it could experience, not the average. Oh, why is that? Well, do I really have to explain that? So political agreements such as the Paris 2015 are aimed at the averages. We prepare for what seems to be the most probable outcome. But even there, we're only giving ourselves one sigma, 66%. And a number of people have pointed out, would you get on an airliner if you knew it had a 34% chance of crashing? Probably not. So again, the question is, how quickly can this happen? So just quite quickly draw your attention to a very important study that was published by Jason Box, glaciologist Jason Box, and a list of colleagues back in 2022 in Nature Climate Change. I've met Jason Box a few times. He's one of the top glaciologists in the world, and I mean, incredibly smart guy who knows the physics of ice sheets extremely well, and has spent way over a significant portion of his adult life he's spent on the Greenland ice sheet. So what they've done in this paper, to give you the very short version, is that they've done an inventory of the amount of ice on Greenland. And as you know, so an ice sheet is in what we call dynamic equilibrium. So ice flows toward the sea at a certain rate. So some of it melts, some of it evaporates a little bit, not much evaporates, and some of it calves into the sea. And then if you have a stable ice mass, it has to be replaced by snowfall. So if the snowfall and the loss of ice are roughly balanced, the ice sheet can be stable for a very long time. So what they've done is looked at the amount of ice that's on Greenland right now. They have looked at the climatic conditions that we are currently experiencing. And this is as of 2022, right? And what they show is that given our present levels of temperature, other climatic conditions, there isn't enough snowfall to replace all of the ice that's currently on Greenland. Now, this ice hasn't melted yet, but it's a journalist called it zombie ice, or you could also call it dead ice walking. It's ice that it's still there, but we know that under current climatic conditions, it can't be replaced. because there's just not enough snowfall. That's the point. So their calculations show that at our present temperature levels, we're already committed to plus or minus 27 centimeters of sea level rise from Greenland alone. Now, this does not take into account any further loss of ice from Greenland due to increased warming. It does not include anything from Antarctica or any other source of meltwater. It's just talking about Greenland. And Box's opinion, which he's expressed in a number of his videos and blogs and things like that, his opinion is the only thing at this point that could possibly prevent the loss of this ice, this 27 plus or minus centimeters of ice, would be some sort of rapid cooling, especially with the Arctic, possibly coupled with massive and immediate carbon dioxide drawdown. And in a couple of places, Box has stated that CO2 removal must become, as he puts it, the project of the century. And of course, you don't see anybody rushing to follow this advice. But if Box and his colleagues are right, and there's a very good chance that they are right, it's not good enough to reduce emissions, right? So we'll talk about that. So now, if you look at this report, State of the Cryosphere report, I found there was a certain ambiguity in it. It's a very hard-hitting report, but I still find they're waffling just a little bit on the status of 1.5 C. So they say, quote, 1.5 C is not simply preferable to 2 C or higher, it's the only option. And yet they also state that even at 1.5, we would eventually be liable to significant sea level rise. And very important, this is something really important that I just haven't had time to talk about yet, acidification, disastrous levels of acidification in the high latitudes that would cripple the oceanic food chain due to dissolved carbon dioxide. And this is a very important effect of anthropogenic carbonization that's independent of temperature. And it doesn't get enough discussion either. So maybe even this report, although it's written by some of the absolutely top people, including Richard Alley himself, and maybe there's even a little bit of scientific reticence appearing in this report. Because what one can say, here we are in January 2025, as of this point, we're already at or over 1.5 C. And we already know it's too much. Even where we are now, it's causing very undesirable effects, right? But not only is it causing undesirable effects now, like forest fires, stronger storms, droughts, all floods, all those things, right? Because we are getting into what the glaciology shows is that we're getting into the region where there's an extremely high risk of triggering those irreversible collapse mechanisms. Yeah, I should watch my time. I'll be wrapping up a couple more slides here. And let me see, where am I now? I'm on slide 25. I'll talk fast. So we're already too high. So some takeaways from this. It is obvious long-term climate policy cannot be based on an acceptance of a 2C temperature anomaly, let alone anything higher, since this guarantees sea level rise that would wipe out global civilization as we presently understand it. Okay. And even an anomaly of 1.5 is sufficient to lead to extremely damaging sea level rise and lethal levels of acidification. Right. So in my humble opinion, long-term policy must be based on holding the temperature anomaly to no more than 1 C. And even at that level, we can't be sure that we would preserve our present coastlines because of the huge amount of excess heat that's already trapped in the oceans. And again, most people here will understand that over 90% of the excess heat trapped by the human-caused greenhouse effect ends up in the oceans. So I'm saying what many people are now saying, we must take active measures to cool the planet down. That's a very large discussion. Just conclude one suggestion I would like to make in terms of policy. Maybe the whole idea of using temperature goals as benchmarks for climate policy, maybe that whole idea is just a mistake for a number of reasons. First of all, the feedback is too slow, so it can take many years to see whether policy is effective. So especially if you say things like, oh, well, we can't be sure we've crossed the 1.5 barrier until we wait 5 or 10 years to see. Well, so you enact a new climate policy and then you wait, and then your grandchildren know whether or not it worked. We'd like something that's faster response. Temperature is too far away from the base of the causal chain, and it ignores effects of carbonization, particularly acidification, that are not directly temperature dependent. So there are other possible metrics that we could use for climate policy. The obvious one, which a number of people, I think including Paul Beckwith and Hansen himself, have advocated, use CO2 concentration. We should formulate our treaties around achieving a certain CO2 level, not a certain temperature. CO2 can be measured easily by any country, and also you get very rapid feedback, so you can find out very quickly whether or not some particular policy or thing you're trying works. And it's much closer to the base of the causal chain for climate change. Or how about just using sea level rise itself? You know, so maybe use that as our metric. Let's fashion our treaties so that we all agree to do whatever it takes to stabilize the seas. That'd be a pretty tall order in itself. So I'll just now, one thing I've got to mention, because somebody's probably going to ask me about this, why not just admit that we are doomed? Okay. The best statement I've seen about this was made recently by David Suzuki. He's quoted in quite a good video made by Bill Ripple last year. The only thing that gives me hope is that we still don't even know enough to say it's too late. So I'm not saying ignorance is bliss. I'm saying ignorance, our ignorance indicates that we might still be able to figure this out. I'll tell you what really worries me. Second last slide. Here's what really worries me about the climate issue. There's a cynical old saying, we have the morals we can afford, right? So you have writers like Naomi Klein, her book, This Changes Everything, who argue that the need to respond effectively to climate change will demand or require humanity to cooperate in a fair and just way. That's the only way we could do it. So in the process of responding adequately to climate change, we will resolve economic inequalities. We'll hopefully get beyond the predatory nature of many human interactions. And I'm not against that, that's for sure. I think it's a wonderful idea. However, here's what worries me. As we get closer and closer to stark emergency, it will be harder to respond in a way that is just and equitable. The solutions are more likely to be imposed in a brutal and technocratic way. And we might squeak through the bottleneck, the climate bottleneck, only to be left with a world that is even more inhumane and unjust than the one we now enjoy. Okay, last slide. And this is a wonderful quote that I made by Henry Pollack. Now, Pollack is himself, he's actually a glaciologist, unlike me, but I'm a philosopher, and I can tell you that I think, speaking professionally, this statement is pretty good philosophy. So Pollack said, nature's best thermometer, perhaps its most sensitive and unambiguous indicator of climate change, is ice. When ice gets sufficiently warm, it melts. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened by ideology and carries no political baggage as it crosses the threshold from solid to liquid. It just melts. And that's the reality that we're all faced with right now. Okay, I'll stop there, and hopefully there's some questions. I'm very happy to take.
Thank you very much, Kent. Paycor has an enormous range of disciplines. It's a think tank, but it's unusual. We have everybody from anthropologists to zoologists amongst our membership. probably dominated by folks like me who learned something in the natural sciences, but then have got concerned about how we carry our understanding, our knowledge into the political domain. And it takes a professor of philosophy to help us do that. So thank you on that basis. Now, John McClintock, would you like to please turn on your video and turn on your microphone, followed by Rob Samulak, and I'll come to you as soon as you've done that, John McClintock. Are you ready to make a comment or ask a question?
Yes, well, Kent, that's all very, very fascinating, and I've learned a lot about ice, which I did not know earlier today. So thanks very much. Of course, I'm sure I'm not the only one who shares your apprehension that when it comes to the crunch, as it were, very draconian and dictatorial measures might be put in place, which cause a lot of secondary effects, which are very brutal, which are very sudden, and which cause a lot of social and political tensions. Now, my question, which I have for you, is let's think how we might slow down the emissions of greenhouse gases into the atmosphere. What would you think about a program whereby households in Canada and in other jurisdictions were rewarded, probably with cash, for bringing down their emissions of greenhouse gases by, say, 10% per year for the next 5 years? I mean, that would in principle halve a household's aggregate emissions. This is just an idea that, I mean, I'm living over here. I'm not actually living in Canada. I'm living in Europe, and it's an idea that we are just beginning to discuss over here, that households could be rewarded for bringing down their aggregate emissions. And aggregate emissions means emissions from domestic activities, emissions by the firms in which one holds shares and for which one is responsible, and one's share of government emissions. What would you think of that? I mean, I don't know if it's discussed in Canada at all, but that's an idea that we're discussing over here.
Something like that, as far as I can tell, would certainly help. And you can start to quibble about, well, where would they get the money? And you would inevitably have political reaction to it. It's like, it would be analogous to the anti-masking reaction, freedom, I should be free to burn as much fuel oil as I want to, and so forth. But I think it'd be worth, certainly there's a whole bunch of things that can be done to reduce consumption. Couple of issues though. First of all, a lot of the big emitters, first of all, there's the military, which is they're huge emitters around the world. I recently saw an estimate of the amount of emissions that the Gaza war is costing. I forget the number, but it's colossal. It's not only from all the tanks and fighter aircraft, but also apparently the US military transports taking ammunition into Israel produced an incredible amount of greenhouse gases. So, and it's been very clear. So one thing that's been left out of all discussions is, because my understanding is the US just would not permit people to discuss this, is emissions from the military. But the bigger problem is, if what the physical picture that a lot of the glaciologists are presenting us right now suggests that emission reduction is not enough. Now, most people who advocate climate policy, they're all focused on emission reductions, and they're very leery of carbon dioxide removal for a number of reasons. And so, for example, this Cryosphere report says, oh, carbon dioxide removal may be important after 2050, once we get the technology up and running. But by 2050, we might have lost the Bentley Trench. So the general picture is that if there were some way to do it, if you could just press a button and make it happen, we should reduce CO2 concentration to 300 parts per million. This afternoon would be good, you know. And nobody has any idea how that could be accomplished. But the trouble is, if you just say, well, let's have all households reduce their emissions by 10 or 20%, of course that would help. But it's almost a drop in the bucket compared to the magnitude of the problem. Is that we're already well over 400 parts per million. We're increasing 2 to 3 or almost 3 million, sorry, almost 3 parts per million per year, right? And people turning down their thermostat a couple of degrees is just not going to be decisive in stopping that. Okay.
Well, if you don't mind me saying, I'm not suggesting that people turn down their thermostat by 2 or 3 degrees. I mean, that's a trivial, as you say, a drop in the ocean. What I'm suggesting is that people every year for the next 5 years cut their aggregate emissions by 10%. And,
Sure.
they are incentivized to do this with reward, you know, maybe $1,000, $5,000, $3,000, $5,000.
If you can find the money somewhere, I think it's in principle could be very helpful. But the other question that you have to ask is, okay, well, let's say I'm a farmer. What else am I going to drive my tractors with? But
I'm going to have to go and get my calendar, and that's downstairs. So you just have to wait patiently for me because I don't walk very quickly. So just a moment.
Sorry, I'm not sure what happened there. But John, have you completed your question?
Well, I have. I would like to discuss a lot more, but I know there are other people waiting. So
I don't have a long list, so if you're able to stay, I can probably come back to you.
Yes, okay. I would like that.
John, if this is David, I'd like to interrupt for just a moment. It was Valerie Hume who had become unmuted. I've muted her, so you should be able to continue.
Well, I will stop asking my questions, but if I can come back,
yes, I'll
I
try
would very much like that.
We've got at least 20 minutes. Kent, you talked about measuring, that government should be measuring or looking at the measurements that are already made. I mean, there's a famous axiom in manage. You cannot manage what you cannot or do not measure. Here in Canada, the only measurement that is made by our Canadian government is the amount of emissions that we do annually. That's a requirement of the United Nations Framework Convention on Climate Change.
Right.
It is such a cumbersome process that we shall not get the report of our emissions in 2022 for another couple of months or possibly 3 months. That you cannot possibly manage government programs with that kind of
you need
measurement.
And
you talked about paying attention, I think, to the current level and increasing level of atmospheric CO2. It seems to me that that policy needs to be broken down into pieces. There have to be a whole series, at least 10 programs that can be accurately measured on a yearly, possibly a quarterly basis. Say you had a target for for electric vehicles and charging stations, 2 targets. StatsCan already measures the number of EVs measured. And although our government has now made a step in the right direction, it gives significant payments to people who buy EVs, both provincially and federally. We don't know how many, at least I don't know how many cars they actually. So if they were meeting their target of the number of cars sold and they checked it every 3 months or at least once a year, then they could adjust that particular program. Do you see anything like that being useful?
Oh yeah, I mean, I think the general point is that we need a tremendous amount of monitoring of a whole range of economic and climatic and environmental parameters, and both big ones and the little ones. See, satellite technology's gotten incredibly good now, so that they can, from a satellite, they can literally spot a pinpoint, a point source of CO2 emissions or methane, right? So, but there has to be the political will to put these things in place, and of course the money has to be found too. Now, I think at this point the political will is probably the biggest question. Like, people have to decide that it's important, and there's all kinds of parameters that we could measure. I mean, you could literally measure, I don't know, the emissions of each individual city and town in Canada if you wanted to. That could be done, but nobody's prepared to do it. So Hansen's made this point a couple of times, that there's been various atmospheric monitoring missions that he's proposed to NASA, and then their budget gets cut for essentially political reasons and then lost in the shuffle. And so you end up that climate scientists themselves are often flying blind on, we're trying to make predictions on which the future of humanity could depend, and we don't have enough data. So yeah, absolutely. Whatever particular programs we enact, we have to measure the consequences, and it has to be rapid. One thing I like about using CO2 as a metric is it can be measured locally. The equipment to measure it is cheap and readily available. I have a friend who's an engineer who was telling me how he measures CO2 levels he has to look after the sort of heating and air conditioning and things like that in various schools and a school board, and they measure CO2. You know, it's just something that engineers in a school board can do. It's not sort of something that costs $1 billion to do. So you could have networks of CO2 monitoring stations all over the planet, and they can be updated on a 24-hour basis, right? And so if combine that with various kinds of satellite measurements, you can just take the pulse of the planet very, very accurately if you have the political will to do so. The technology's there, right? But getting back to the previous question, part of the problem with moving off of fossil fuels is that some people will say, oh, we can do everything with renewables. For example, there's an engineer at Stanford named Mark Jacobson who's produced various very detailed calculations showing how we can replace all kinds of sectors of our energy economy with renewable sources. Other people will say, no, it's a bit difficult. It's certainly what I'm going to, my farming neighbors here in Alberta are going to say, what am I going to run my tractors on if I don't have diesel fuel? I mean, if there were a battery that could run a large tractor and combine, they'd probably take it, but the technology doesn't yet exist. So another part of this whole story has to be very significant investment in replacement technology of all sorts, and the R&D that has to go into that. And what we're doing here, I think the problem is the way we think about economics, that we have this sort of fantasy that everything must be done by the marketplace. If there's market demand for something, then don't worry, it'll be fulfilled. And in the real world, it doesn't work that way. You do need government leadership and government public investment in things like, fine, let's develop better batteries. Well, you can't just leave it to private investors to do that. You're going to have to put some significant public money into that as well. And then you might start to get results. If you fund that on the scale that the military is funded, I mean, my God, most people here will know the US recently launched a new, their latest nuclear powered aircraft carrier. I think it's called the Gerald R. Ford, $13 billion ship, right? So that could pay for a lot of battery research, for example, if we thought it was worthwhile. So anyway,
okay, thank you. Fernand Faulkner, would you kindly turn your microphone and video on, and I'd invite Claude Butner to take the floor, please.
As I put in a note, that comment shouldn't go ahead of the other questions, including some very good ones Dave and Paul picked with. So I'm going to forego that.
Okay. Fernand, please make your point or ask your question, or both.
Well, I'm listening to all these talks, and I really don't have questions. I do have some background in geology, and but that's it. And so I'm in a phase of getting up to speed with the thinking inside KCOR. And so my questions are always how to speed up the reactions of the general public to the current crisis. And I'm mulling over that. And recently there's been a discussion on KCOR climate. It was about how humans had this lemming-like behavior, and that would doom us. And then there was an excellent paper by Bill Rees and many others. And in that paper, they talked about the need to mobilize and use the science and the knowledge of marketing to align people to, and that doing that, you could establish quick change. So yes, those are the thoughts that I'm having as I'm listening. And I'm sorry, I'm not questioning. I think that it's an excellent presentation. I've learned a lot. I've been to the north. I've seen calving, and so I have an experience of the ice, and but I don't have the deep knowledge that was presented today. And I guess so where my passion comes from is to address it in the human sphere.
Well, thanks thanks for your comment, and I can't disagree with that. I trying to see all aspects of the problem, and the human sphere is a very important dimension of the problem, but in many ways that's harder. It's easier to talk about techniques of carbon dioxide removal than it is to talk about how do you get people to agree to do something. And I mean, another problem is that some governments in the world, I mean, for example, in the UK right now, climate protests are essentially criminalized, right? And they just want to shut it down. And you could march on City Hall with a sign, and you could end up wearing an ankle bracelet, So it's very, very difficult, and I think we just need as much communication, as much public education as we possibly can, and make people aware of things like, okay, there are these things called marine ice sheets. Well, what is it? Why does it matter to us? Mm-hmm. And I think that's what I try and do, is I try and just see the big picture and put it all together. But anyway, should take some other questions, I guess. Sure.
Paul, thank you. Paul, would you like to turn your microphone on as well? And the final question will follow from Dave Doherty. Paul, please.
Yes, thanks, Kent, for your great talk.
Thanks.
One
Enjoy
thing,
your videos, Paul. I learned a lot from them. Thank you.
one thing you might want to talk about is the, I call the baseline 1850 to 1900, baseline 2. The
Yeah,
original baseline 1 was 1750.
sure.
So when the IPCC talked about pre-industrial, they talked about 1750 initially. Now, the
Yeah.
problem is that there's if you just look at the plots, there's about a 0.2 to 0.3 increase of temperature
Sure.
from the initial baseline to the second one.
Mhm.
So you have to keep that in mind when you're talking about 1.5
Yeah.
and 2.
I didn't want to
Um,
get too technical about that in
yeah,
my talk, but yeah,
yeah,
the
yeah.
issue of baseline is obviously is crucial too,
Yeah.
and I was just
Another,
sticking with the IPCC because
right.
that's what is usually discussed
Yeah.
these days. But yeah.
Now, another point is on the isostatic rebound. You do talk about it, but I don't think people realize how large it is. So if you've got 3 kilometers of ice on the peak of Greenland, the instability in equilibrium, the bedrock is pushed down 1 kilometer. So we're not talking about small amounts. We're talking about
Yeah,
a third of the ice thickness. And that comes from the simple fact that the density of ice is about 0.9 and the density of bedrock is about 2.7. So a 3-to-1 ratio. That's
Okay,
in
so
grams per
time
cubic centimeter.
factor is a big question here, though.
Yeah,
Like,
yeah. So
how
time
long is that going to
factor,
take to bounce up, right?
exactly. It takes. I guess also, is it asymmetric? Does it take as long to push the bedrock down as it does for it to spring back up? And those are important issues.
What I'm trying to emphasize in my little talk here is the things that could matter in the short to near term scale. Now, isostatic rebound, of course, is important. It's a real thing, but it
Yeah.
can take thousands of years for a
Yeah.
landmass to fully rebound. And
Yes.
so that's why I was focusing more on things like ice cliff instability and marine ice sheet instability,
Yeah.
which could happen overnight and
Yeah.
in a way that is very difficult to predict.
Yes. Now, Hansen, years ago, Hansen predicted a 5-meter rise of sea level by 2100. 5 meters, not 1 or 2 meters. I don't know if he's backed that down a bit. It's worth asking him. I mean, I kind of asked him. I had an interview with him about a month and a half ago, 45-minute interview. It's on Climate Emergency Forum. And I asked him, but he kind of skirted the question a bit. So I think his next paper, he's probably, he'll be talking more
I saw
about
your
that.
interview, and I thought it was very good.
So,
That they're working on something, and that's I want to see
yes,
that paper when it comes out.
And also, I think a lot will be in his book, Sophie's Planet, which should be out at some point this year. It keeps getting pushed back because of his other work. So, and it's interesting that he decided at the last minute not to go to COP28 in Dubai. He actually flew from the US to Amsterdam, and it was at the Amsterdam airport that he decided to do a U-turn and go back home rather than go on to Dubai. So
that's interesting.
Obviously, he was very concerned about some of the statements coming from the COP and their push 1.5 alive. So it wouldn't surprise me if a baseline 3 appears subtly, 1980 to 2010 or something like that. And then, we're only at 0.8 degrees of this new baseline. And that, it's sort of a game that's being played by policymakers and governments.
Yeah, no, that's right.
So anyway, thanks again for your talk.
Thank you. I guess the other thing I'm trying to emphasize here is, again, you can have various projections of sea level rise based on various emissions trajectories, right? And there's I forget the RCP, those representative concentration pathways, and I forget all the numbers, but there's what I think is really worth, if you want to talk about baselines, here's a good baseline. Take where we are today, January 25th, 2024, at our present CO2 levels, at the present amount of heat that's in the oceans and the atmosphere, the present heat imbalance, just where we are today. And let's say we somehow miraculously stop all emissions from this afternoon onward, how much sea level are we already committed to just where we are
Yeah.
now?
Well,
And
I mean,
so Jason Box has
yeah,
given
yeah.
a partial answer to that question,
Yes.
but that's
Yeah.
a good question to
Yeah,
ask.
yeah. I mean, also mention, I mean, sea level rise is a problem last month, this month. I mean, the whole coast of Maine is being hit with exceptionally high water levels. Last month, it was the coast of California. There was a huge surge of the ocean in the Marshall Islands, which just basically flooded out a US base there. That happened just yesterday. So there are there's anecdotal evidence of people on the coastlines having trouble already from exceptionally high tides combined with storm surge. And of course, it's on top of sea level. But anyway, thanks again.
Sure.
I'll mute myself now.
So, Dave Doherty, would you like to make the final point in the recorded part of our conversation this afternoon, please?
Sure. Thank you for the talk, Kent. I made a number of observations. I put in a bunch of links about some of the things to which you were talking, and you might want to review them later when the chat comes out. I had 4 questions, and I want to
Only 4?
limit it only to one, okay? Because I think this is actually the most important question. And it has to do with solar management, let me call it, and atmospheric CO2 concentrations. So given our failures with most technologies and the many unintended consequences of virtually all of them, I wonder if it's reasonable to expect, do you think it's reasonable to expect that we would be able to reduce atmospheric CO2 concentrations and or temperatures through solar management? You know, putting sulfate into the atmosphere, putting up giant sunshades, whatever it might be.
Okay. Oh, okay. Well, it was a really large discussion, and oh man, where to start here? So, a couple of points. First of all, solar radiation management, what it means is doing something to block sunlight, and there's a whole bunch of different techniques that have been proposed. The one that everybody's scared of is putting sulfate in the atmosphere, but on the other hand, it's also one of the easiest things to do. So that's one of the reasons it might end up being done. Any such technique in and of itself does not reduce CO2 concentration. It just helps to cool you off. So it's like we're carrying a parasol, right? And as a lot of people have pointed out, so solar radiation management, I think is best viewed as an emergency technique. So for example, Sir David King has been arguing that we have to cool off the Arctic, and they're looking at things like what's it called, marine cloud brightening, as a kind of a temporary fix that might help for a while. But the deeper problem is this CO2 level. And the CO2 level, first of all, it contributes to temperature increase in well-established ways, and also it contributes to the oceanic acidification, which is very, very threatening to. So the lower pH levels, higher acidification leads to little tiny marine organisms can't form their calcareous shells anymore. They literally dissolve. I mean, think of how do you get scale out of your kettle? You know, you put some vinegar in it, right, and it dissolves all the scale. So at a certain point, and these little tiny organisms are the base of the whole marine food chain. You know, all the way up to whales and things like tuna and salmon that we like to eat, they're all dependent on small calcareous organisms. And if the acidity gets too great, they can't survive. So I think in the long run myself that it's more important to look at carbon dioxide removal techniques. And there are some that are very promising, but they're, number one, even the ones that would work well are colossally expensive. So you're looking at nuclear aircraft carrier levels of expenditure, right, to put in the technology that would be needed. And secondly, any method of carbon dioxide removal is just, the physics of it is necessarily energy intensive, right? I mean, just think of the process of, you've got some gas, trace gas, dissolved in the atmosphere, and you've got to somehow pull together all that atmosphere and remove the trace gas. It's just inherently hard thing to do, right? And now but still, I think that there is some promising work that's been done in direct air capture, and the one that interests me a lot. There was a very good article in Scientific American on this about 2 years ago. There exists a class of minerals, so certain basalts, and then there's another. It's a mantle rock called peridotite, which sponge up carbon dioxide with amazing effectiveness, and without getting into the whole details of how it works, it would be feasible to have. Some people have done the math on this. It would be feasible in principle to have giant plants sucked in the air. You dissolve the CO2 in water, you pump the water into the rock formation, it gets absorbed into the rock, you recover the water. And what you basically do is the carbon dioxide turns into limestone, right? And it's permanently mineralized at that point. And it could be done, but it's, again, multiple tens of billions of dollars of expenditure. I mean, you're talking about infrastructure that's probably comparable in size to the fossil fuel industry. And there's a few pilot plants here and there, but nobody's working on it seriously right now. And so I would say, yeah, it's possible. But I mean, if you want to be a devil's advocate here, that, I mean, we don't even, let's say we could do something that, just being science fictional here, in the next few years, we could reduce the CO2 level to, say, 300 parts per million, on virtually pre-industrial level. It's not clear that that would even solve the problem, because there's still so much CO2 dissolved in the oceans, so much excess heat in the oceans. All of that has to diffuse out. And would the excess heat diffuse out before it undermines those marine ice sheets I was talking about? Because what's making them melt is the heat that's in the ocean. But this is what people find hard to grasp. You look at Thwaites Glacier, and on the top of it, it's 40 below zero, right? And you think, what could possibly go wrong? It's really cold there. But underneath the thing, it's +2. And that's what's killing it, right? So it's the heat in the ocean. And even if we did everything that is even remotely technically or physically feasible, would we get all of that heat out of the ocean in time to prevent multiple meters of sea level rise? And the answer is, we don't know. We just don't know. So
Kent, we're going to wind up the recorded session in a moment. I'd just like to remind everybody that the recording of this presentation is almost certainly going to be posted this evening before Art goes off for supper, and maybe David as well. And it will also include a PDF of the slides, which I'm sure many people will find useful for future use. So John McClintock, I don't have time to fit you in now, but I expect Kent will be with us once we've signed off. And so please stay around and ask him your question after Ted Manning has thanked our speaker. Ted?
Thank you very much, Kent. Another very good presentation in our series. I'm a mix between a social scientist and a physical scientist, so I actually understood most of what you said, but I'm also coming right back to what John said, one of the very first questions, which is, how do we make people change their minds? And we're really coming back to that on any of the solutions. The problems, I think, are very convincing. The solutions less so, and yet without getting some people at least to buy in, even those militaries we've been talking about to buy in, how are we going to make them do something? So I'm going to end with one or two things. It does work at the small scale. We have success stories. Right now you can actually breathe the air in Beijing, and the reason you can breathe the air in Beijing is real-time monitoring at each intersection put in by their government to tell them whether they're allowed to breathe or not. And that got cut back very fast, even in a society that's very controlled. They brought so much pressure on the governments, and the governments then put so much pressure on the local industries that you can actually breathe the air in Beijing. And there are other examples of this at a very small scale. People only, I think, take things seriously when they see it themselves. And certainly Greenpeace started that way. Reason that they got controls on water quality in beaches almost all around the world is because Greenpeace and its friends in Vancouver didn't like not being able to swim in the beaches in the summer because they were closed because of contamination. And now we have systems globally using the blue flag symbol that tell people which beaches are clean. And there's a real economic message, and it's a really personal one. Even if your place is going under, however, these days, I've got friends in Miami who don't give a damn. They're quite happy to build themselves a new condo right on the beach. So we do have a serious issue of comprehension and how that trades into actual action. Even the kinds of things John said, where we sell everybody on actually doing something, is exceptionally difficult. Anyway, that's my diatribe today, and it was stimulated very well by Kent and with some very good questions from our other folks. So I would like to thank you particularly to contributing to this nice dialogue we are having. And this will continue, and one day we might get lucky and come up with the panacea that we all seek. So I would ask you all to come out again next week and in following weeks. This will be, as you've been told, available very shortly on our website. And we would also ask you please to subscribe to our YouTube channel. It gets us more views. We're up to several hundreds or thousands at times. So we are actually able to influence some people's attitudes and perhaps their actions. And finally, I'd say if you don't belong to KCOR, please do. This is a very good public service that we're providing at an exceptionally low cost from some very highly qualified people. And to the very least, please help us keep this going. So thank you all very much, and we will see you again next week. And we will now turn off the recording, and we can just chat on any other issues we may wish. And for those of you who have not spoken, please do. Thank you very much again, Kent.